Hello, everybody, and welcome to tonight's event. I'm sorry about the slightly late start, but it's good to have you with us. So my name's Julian Huppert. I'm the director of the Intellectual Forum here at Jesus College. We will be recording this event for people who couldn't make it. Now, these are, of course, very strange times. It's the evening of the second coronavirus lockdown, and certainly outside my window, and I think other people's as well, we see fireworks brought forward from tomorrow. It's also the day after the US elections, and the world is in a very funny place. But how do we know anything about this? We can't see a virus, we can't see an entire electorate. How do we know what's true and what isn't? Unfortunately, we're really lucky to have one of our own fellows, Ulrich Schneider, to talk about how we detect things in contemporary science and whether seeing is believing and what we would mean by that. Now, Ulrich is a regular for us. He conducted the first experiment in our lovely Frankopan Hall, demonstrating his work on ultra-cold atoms, things that are even colder than outer space. And so tonight should be a fantastic talk as well. We're going to hear from Ulrich first, and then there will be lots of time for questions. Please either put questions in the Q&A tab that you should be able to see, or raise your hand on the participants tab, and I'll try to bring you in and manage all of that. Just before we start, I should point out we have lots of other events coming up online. So next week on the 10th, we're talking about different types of mind with Dr. Temple Grandin, who's world renowned for her trailblazing work as a spokesperson for people with autism and also for her work on animal behaviour. Then on the 14th, Matthew Young, one of our college postdoctoral research associates, will be talking about the genetic origin of cancer. And there's much more. So as ever, please do keep an eye out for us on Eventbrite, Facebook, Twitter, or join our mailing list. Ulrich, thank you so much for joining us. Over to you.
Thank you very much. Can you see my screen? Perfect, very good. Yes, it's very strange times indeed. So we picked this date because it was originally scheduled for, I think, March, but then we had the first lockdown hitting. So we picked this date. And I was basically approached in summer and asking, like, which date in November would work for you? And then we looked at this date and said, well, why not this one? And of course, it couldn't have been a more stranger day. Indeed, we are preparing for another lockdown. That's also why everything was very last minute with the preparation. But now here we are, and we can talk about seeing is believing or not. So let me see if this all works as it should. Let me start with a simple question. Do you believe in something you cannot normally see? Do you believe in atoms? And of course, most of us will believe in atoms because they have been told in schools that atoms exist. But how about if you're skeptical? How can you convince yourself that atoms do really exist? And actually, we're now very fortunate because we can now see them. So what you see here is an apparatus in Oxford. It's a so-called ion trap that can, like in the middle here, between these electrodes, can trap individual ions, so individual atoms where you've taken away one electron and have given it one electron extra. And if you look at this, let me just zoom in, you can take a picture of this one. If you hit it with a laser beam, the atom will fluoresce. It will emit light, and this light you can record on a camera, or you can see it with your bare eye almost, and therefore you can say, yes, there is something. How do you know that it's a single atom? Well, if you take a big piece of material, you would think it's shorter, you can make it smaller, smaller. But here at some point, you will just get a certain amount of light corresponding to one atom. If you try to reduce it, it will drop to 0. So it's either 0 or 1, or 2, 3, 4. You can have more than one ion in there. So it's now very easy for us to convince ourselves that atoms do actually exist, because ions do actually exist, because we can see them. We can see an individual ion here. And now, of course, once researchers have like such a nice trick, they try to do more with this. And there's a group in Paris, Institut d'Optique, Anton Prouvé. They can now trap individual neutral atoms, and they can take like hundreds of them and arrange them in various different patterns. And they do like a lot of nice things that you would want to do. You would want to see a sphere, whatever you want. Or if you don't trust me that they sit in Paris, you just look what they do here. They built the smallest Eiffel Tower possible, I guess, 126 atoms. So yes, atoms do exist. I've now convinced everybody that atoms should exist. If not, we will have a very interesting discussion in the chat afterwards. And why is this important? Well, if we think about it philosophically on how science works, natural sciences, shall we say, we start with an hypothesis. We start with our theory, with our current understanding. So I could have the theory that atoms do not exist and that actually matter is continuous, because always I can take a big piece of metal and I can chunk it in smaller parts. And I can keep on dividing it. So why should it stop at some point? I can make the prediction that it will never stop, that it will always be able to make a smaller part, smaller part, smaller part. And the good thing about this prediction is it's falsifiable. So I have a prediction that I can falsify. I can do an experiment, one experiment, and test this prediction. And then, of course, two things can happen. The first thing that can happen is that the prediction is right, that the experimental test follows what I would have predicted from my theory, and that then tells me that, yes, this hypothesis maybe has some merit. A single pass test, of course, doesn't prove a theory right. You'll have to do many, many, many tests. And in the same way, also, if we have a theory that is a prediction that is totally wrong, that you can falsify, then in principle, you should say, okay, now this hypothesis must be wrong, and I have to come up with a different one. There's a lot of fine print here, of course. Things are not that easy, because if we now say, I make an experiment where I try to get reception with my mobile and I don't get reception, that does not mean that electromagnetism is wrong. It might simply mean that just something went wrong with my experiment. For instance, my mobile is switched off, or I'm just out of range. So there's many things that can go on. So there's always the question of, do I interpret my experiment correctly? Do I know what I'm doing? But if I do my experiment very, very well, in principle, in physics, as in all experimental sciences, the experiment is the ultimate arbiter of truth. And this, of course, means we have to be very, very clear about what do we see, what can we see, and how do we interpret an experiment? How do we analyze our experiments? How do we know that what we believe we see and is really what is there, and that we're not fooled by anything in our vision or in our apparatus? And of course, this being Cambridge, and I'm giving a talk about physics, I have to start somewhere, and I have to start with Sir Isaac Newton. And you know that one of the things he did was also doing a plague, probably a more stronger plague, the plague, so he was not in Cambridge at that point. He was sitting on an apple tree. And it's not the apple tree in front of Trinity College, because he was not in Cambridge at the time. And I was told that this is the picture of the correct apple tree that was still there during Newton's time. I'm not 100% sure about this, but it's not important. It's an apple tree, and you will have apples. And then what Newton did is he observed gravity, and he saw that this apple fell down. And if I now come back to whether do I see what I believe I see, Newton didn't have to worry about it. He was pretty clear this is an apple, and this apple is falling downwards. And I think on that level, it's very easy to say, yes, we trust our eyes. If we see this as an apple, if we see it's falling down and not upwards, then that's the truth. Can we always be sure about what we see? Let's take this picture and take a second to look at this and think about what you are seeing. And about half the people will say, well, that's obviously, it's a bird, potentially a duck. And here I can see the beacon or the bill of the duck. The duck is looking to the left. This is the eye. It's obviously a duck. But the other half of the people will say, no, this one is obviously a rabbit. And the rabbit is looking to the right. So here's the mouth of the rabbit, and these are the ears of the rabbit. And this kind of cartoon is well known as the duck rabbit, because some people will see it as the one, or other people will see it as the other. And which one an individual person will see is kind of hard to predict. And it's like full of biases. It's full of various factors, for instance, the time of the year. So here was an experiment that was done in 1993, where they basically said, okay, let's show this picture, it's kind of the cartoon version of it, to like a couple hundred people and ask them, do you see a bunny or do you see a bird? Or well, actually they asked them, what do you see? Just tell me. And if you look at the first age group, 2 to 10, more than 90% of them said, I see a bunny. And just a few percent of them said, I see a bird. If you look at older people above the age of 10, well, it's maybe 70-20, but still pretty clear. There's got to be a bunny. People perceive this picture as a bunny. But maybe that's not true, because this is an experiment that was done around the Easter time. They then did the same experiment again in October, so at the time of the year that we just went through, where you have a lot of ducks floating around on the ponds, you have a lot of birds flying overhead, maybe birds passing through on the way to the south. And interestingly, if you do the same experiment in October, most people say, well, it's some kind of duck, or an unspecified other bird, or a stork, or maybe even a flamingo, anything like this. And just very few people say it's a duck. And the same is true for people age 2 to 10 and age above 10. So it tells us you got to be very aware of your expectation. You got to be very aware of subconscious biases, because just because it's a different time of the year, the picture is the same picture. So we have to keep this in mind as scientists. We have to keep in mind that we're not only looking for the things that we believe we will find, but also looking for the unexpected things. And we have to be very open about that. And that's basically not the main part of my talk, because the main part of my talk is now going to be, well, we're not always looking with the bare eye. Do we not only trust our own perception, do we also trust our tools? Can we have trust in our tools? And again, we start with Sir Isaac Newton with early astronomy. Here is a Newtonian telescope, picture of it. And here's a schematic on how it works. It's basically a curved mirror, which means that all of the rays that come from the distant stars, blue and purple are two different stars here, they're like at almost the same direction, so they come in almost parallel. And then they get reflected from this curved mirror, they get focused down, and then there's a second small mirror here that focuses them out. And here you would observe them, and you would see the blue and the purple one at different positions, so you can discern now the two different stars. And this is a very simple instrument, powerful but simple, and it's actually therefore rather good. And you don't have to think much about philosophy, whether you can trust what you see, because basically scientists could either build their equipment themselves, or at least the equipment was so simple that they could understand it in full. So you know it has limitations, but you know and you can understand perfectly well what it does. And now we'll stop with Newton and we'll fast forward to the end of the last century, and we go to this kind of picture, also from space, except for the laser pointer. And this picture now is the famous Pillars of Creation. It's a picture of basically taken with the Hubble Space Telescope and released by NASA. And if you look at this picture, you can actually start wondering about something. You can wondering about why, if you ask anyone, for instance a kid, to draw a star, they will draw a shape like this, maybe with 4 edges, maybe with 6 or 8. Everybody will draw something pointy when you tell them draw a star. But I don't know much about astrophysics, but I know that stars are the same thing as our sun. So in principle, a star should look like this. It should be a rather featureless spherical ball held together by gravity, like our sun is. So why do we have this perception that a star looks like this, very pointy, and not round and spherical like this? And you can see it actually in this picture here. You can see that if you look at a single strong star here, which is in our own galaxy, I guess, you can see there's these star-shaped, now I already say it, star-shaped protuberances coming around it, these extra lines coming in there. And you can ask yourself, where do they come from? Is there maybe a fundamental difference? Are the stars different from our sun? Because our sun is spherical and the star is star-shaped. And the answer is actually no, it's not. In this case, it's an artifact of the Hubble telescope. And here's a picture from another Newtonian telescope, where you can see this is this curved end mirror here at the end, and this is the front little mirror in the front. And now you can see something crucial. You can see that this mirror in the front is not just floating in free space, but it's held in place by these 4 little metal bars here. And now the structures that we see here, they are called so-called diffraction spikes. And they actually come around the point because light is a wave. So light gets diffracted around these bars, and that gives rise to a diffraction pattern that has the same symmetry as the structure you saw there. And because the Hubble telescope, this is not the Hubble, but the Hubble also has like 4 of these bars here connecting the middle to the side, the Hubble telescope will always have these 4 shapes around it. If you take a picture with a proper camera, you will see maybe 6 or 8 or 10 shapes around it. And that's basically because the aperture in your camera, the stops that you can close down further, they are basically consisting of 6 or 8 plates that come in, so that the opening is not spherical anymore, but say a hexagon or an octagon. And that creates a structure, and the diffraction on that structure gives rise to the star shape. So even in classical instruments 30, 40 years ago, we needed to understand very well how they operate, and we needed to understand their limitations. And we needed to understand on why a picture looks the way it does. So a lot of work in science always goes into instrument development and instrument characterization and instrument verification, that the instrument really measures what we believe it measures. And in this case, in the case of this picture, there's actually even more going on here, because this picture is what we call a false color image. So it's not just a color image taken with a good camera, it's actually The blue shades you see here around, they're proportional to the amount of oxygen in this area of space, while the red one is sulfur and the green one is nitrogen and hydrogen. These are all pictures taken with separate instruments, looking at separate things, and then they're just like combined into this one false color image, false color representation for us to look at. And the scientists did this because they wanted to see, does the sulfur sit at the same spot where the oxygen sits, or are they separate? How do these structures hang together? And if you look at these pictures now, they're very, very beautiful, and they also are very powerful for interpreting things. But they have to come with an instruction manual. You really have to understand what this picture is and how this picture was taken. Otherwise, you're lost. Let's fast forward again, just about 20 years, to 2019. And the most spectacular of all pictures taken by astrophysicists is this one. It doesn't look like it. Maybe it doesn't even look like much. But this is a picture of a supermassive black hole in the center of a faraway galaxy. The galaxy is Messier 86, and then the object is called Messier 87, and the object is called Messier 87 star. And this is a supermassive black hole, or rather the black hole is of course the black part here in the middle. And this is the accretion disk around this, where you have a very hot plasma that emits electromagnetic radiation. And this can be observed from Earth. It turns out that the radiation in this case is not in the visible range, it's radio waves with a very long wavelength of 1.3 millimeters. And it turns out to get the angular resolution that you need in order to resolve this little thing, you need to have a very, very huge baseline. Think of the diameter of your mirror, of your telescope in order to do so. And here you can basically see what they did is they built the biggest telescope you can actually build on Earth, more or less, because they basically took like base stations at different points around the Earth. And by combining interferometrically the signals coming from them in a phase coherent manner, it looks like you have one very, very, very large aperture. And that's how they got this amazing resolution. And from this, it's not only just a nice picture, they can also like make important observations by saying the mass of this thing is on the order of 6.5 times 10 to the 9 sun masses. So the term supermassive really comes into its own here. And if you read the publication, how they went about this, there's something very interesting in here. What they said is to assess the reliability of their results, because of course there's a lot of computation going into this. They said what they did is they built 4 teams, each blind to the other's work, and then produce images using various different methods. And this stage allowed us to avoid shared human bias and to assess common features among independent reconstructions. So the scientists were at this point saying that there's so much going in there and so many potential choices of errors and mistakes in that code that we do not fully trust each other, or we do not fully trust ourselves, I should say. So they split into various different groups, 4 in this case, and they all worked independently of each other without showing each other's what their results are. And then in the end, they compared their results and they said, oh yeah, these features are common features and we see them all. So they're model independent. These features work and these features are therefore reliable. So I think the take-home message of this is taking good care in really, really complex observations and data analysis is possible, but it may require really substantial resource. And so far, my examples have always been about cosmology and astrophysics, because let's face it, they produce very nice images. But there's of course similar things going on in very different areas of science. So this is a picture that made a lot of fuss in the 1980s in the condensed matter community. This is a diffraction picture on a certain material. And here it went the other way around. The picture was taken in a very straightforward standard way. And the interesting thing about this is that this picture has a 10-fold rotational symmetry. You have 10 dots in one of those circles. And there have been very strong, very good theoretical reasons why such a picture should be impossible. There is a crystallographic restriction theorem that tells us that more than 6-fold rotational symmetries in the periodic crystals are impossible. They're just not allowed by nature or by mathematics. So the arguing in this case was now, okay, the scientists must have made a mistake when they were taking this image, something like that's called twinning, because this image must clearly be impossible. In this case, the scientists could show, and other scientists could independently reproduce the results, and they could show that no, these pictures are right. And it turns out, for the experts, that these materials are so-called quasi-crystalline materials, so they are not periodic, but still long-range ordered. So therefore, the 6-fold restriction goes away, and we found a new way of how nature can make materials which can have interesting and different properties. So in this case, we had a very, very strong strongly understood and clear theory, but it became obvious that this theory had a loophole and it needed an extension, which then could be provided. So the experiment is really very powerful in this way, but you need to have trust in that the experiment really shows what it does. And then, like 10 seconds of shameless advertising, this is the area that I work in, and we now could build like artificial systems like this in our lab, where we have an 8-foot rotational symmetry. And in this case, we understand also the structure from one octagon to the next, because we build it with our hands with interfering laser beams, so we know what we're doing. And we can then also create very complex pictures, very complex structures, and still understand where they come from. So if we have a pre-knowledge of what a structure comes from, we can also understand very complex images. Here's another example. This is an image of a condensed matter surface, the real material, the surface, and it's measured in various different ways. And if you look at the picture, if you compare, for instance, this picture, things are relatively sharp, but it looks like it's whole. It's like little holes in there. If you look at this picture, it's just done in a slightly different way in the same machine. Things look a bit more fuzzy, and it looks like you have little pillars pointing out, not pointing in. So again, you can have very different pictures just by operating your equipment in a slightly different way, and you need to understand how your equipment does generate the picture. In this case, this is a scanning method, so it's basically a tip going to a certain point, measuring for a certain while, then going to the next point, measuring, going for the next point, measuring, and then analyzing this data and pixel for pixel per pixel, constructing the image. So you really need to understand what the machine is doing. Then you can have the trust in in your experimental result. So now there's a new sort of doubt coming into the game. Everything is getting much more complicated at the moment. And the reason for that is a very powerful new technique that's either called artificial intelligence or machine learning or deep learning techniques. So in mathematical terms, what the technique does is it takes an input, say a set of numbers, maps them onto one number in each node here, and then it calculates the values in the next nodes by just combining the values from all of those nodes with certain weights. So each of these lines here has a certain weight, and all of the magic is encoded in these weights. Then you go from one layer to the next layer. So there's another set of weights that you can apply to another layer, and then these few numbers here at the output, they are your output. This sounds very abstract, but here's like one example. So your input could be an image. You could take this kind of image, say take a part of this image that goes into like some preparationary stages, convolution layers, pooling layers, and then it goes into some of these fully connected layers. And then the output layers are basically the probability that this picture contains a car or a bus or a train or a plane or a ship. That's the automated image recognition. Of course, something that's now very powerful and used everywhere. And if you use the Google image search, and many other things, you will encounter this almost every day. And you will probably also have helped train these systems and build these systems, because the magic in these systems is to know which weights do I have to apply. And that's basically an optimization process. So what they basically do is they take a training library of, say, 1 billion pictures and having like 100 different or 1,000 or 1 million different categories. And then they train the system. They tell the system, this picture is a car. This picture is a train. And then the system will have to like optimize these weights, these parameters in such a way that all of the pictures where there is a bus in there, the bus light goes on. With all of the pictures where there's a dog in there, the dog light goes on, and so on. And many of you have helped training these systems over the last 20 years by using captchas. Captchas are these little annoying things on web pages where you have to click, yes, I'm not a robot. And sometimes it gives you a little task to show that you're not a robot. So for instance, one example is select all of the images that match this one. So you as a human say, well, this is obviously a cat. So I click on all of those pictures where there's a cat, but not on the one with the dogs or the veggies or something else. And many of you will have seen these pictures by Google many times. You will also have seen the ones where you have one big picture and it says, click on all of the tiles where there is a fire station and a fire hydrant inside or a street sign or anything like that. And it's always annoying. You have to click these things, but it distinguishes you from a simple other system. And it gives them data in the long run to build up these libraries. And with this, of course, they can then do a lot of image recognition and can do a lot of powerful things. Now, we as scientists, of course, say, well, there's a new toy on the block. Can we use this also for our purposes? And this is something that a group in Hamburg has done, Christoph Weitenberg and his colleagues. This was published last year. So what they did is they took pictures from a quantum gas apparatus, I will not explain the physics so much, but these pictures can look very weird. They can look like this. And we know that these pictures, the system can be in 3 different states. And these states correspond to different Chern numbers C, can be -1, 0, and 1. You don't have to understand the physics. You just have to understand that the task now is to take many, many pictures and categorize them and say this picture corresponds to C equals -1. This picture corresponds to C equal 1. And it's very complicated. A PhD student looking at these pictures for a long time could not say, well, this is a -1, this is a +1. It's not very simple. It's a pretty complicated and subtle task. So what they did is they said, okay, let's take these pictures, use first a convolution layer, and then use again these fully connected layers with 3 output layers with a classification of C -1, 0, and +1. And then they went in there and took many, many pictures. So they took in order 16,000 pictures almost for training the system. So they took 16,000 pictures where they said, we know this one is a -1, this one is a +1. And then they trained this artificial network on this kind of data, and then they gave it 4,000 other pictures. And they were asking it, what do you say? Is this a -1, a 0, or a +1? And here is the result they got. So they could like take these pictures as a function of 2 parameters. What they call a phase and the frequency, doesn't matter. They know from theory that everything within this red curve here should be Chern number -1. Everything that's within the blue curve should be Chern number +1. And everything outside should be Chern number 0. And the training data they only took in these regimes where they knew very clearly what was going on. So they took training data here where there's this gray bar, training data here where there's the gray bar, so only at these few points. And then they said, now let's take many pictures everywhere in the space and always ask the system, the artificial network, what do you say? What's the Chern number? Is it 1, 0, or -1? And sometimes it gives an answer like 0.5, which says, I'm not sure if it's a +1 or a 0. But if you look at this, it's amazing. No PhD student could do this, but because the system can analyze like 15, 16,000 pictures and kind of keep them all in its mind, it could then say with almost certainty, yes, this one is a -1, this one is a +1. So this technique is very, very powerful. The neural network can really correctly identify the phases. The trouble we now have is, if we're asking, how does it do this? What does it do? Well, the answer we can give you is, well, it sets all of those weights in these matrices accordingly. So I can give you the full transparency. I can give you the inner workings of it. This is this huge array of these numbers, but you couldn't interpret it. You couldn't make sense of it. Nobody can. So that's the problem why these systems are, in a sense, something new. They are a black box where we know that they do something which is often very useful, but we don't know how they do it. And this kind of systems, they are now everywhere. So for instance, if you now take a picture with your mobile, then most mobile phones nowadays make very, very nice pictures. They're like, if they see a sunset, they really adjust everything such that the colors come out nicely. If they recognize there's a person in the picture, they directly recognize here's the face, and then the face is in focus. Everything else with a bokeh effect is out of focus. So they can make very beautiful, nice pictures. And the way they do this is that they have been trained by neural networks. With neural networks have been trained for them to like detect very, very different situations, very many different situations, and thereby to react accordingly and say, well, in this situation, we should do this. In that situation, we should do that. So there's a lot of automated decision making that we as a user can't really control that's going on under the hood. And we just get a very nice looking picture out. And that's great, except if it goes wrong. So every once in a while, you get a picture where you're like, what is this? Why did the system think that it should now use this mode? Another mode would have been much, much better. So these systems sometimes can go wrong, but very often the systems are helpful. And now let's watch a game of soccer. This is a game that was played in the Scottish Championship just a few weeks ago. And let's just watch this video for a little while and see whether you see something out of the usual. It's various different scenes cut together, but you should see one thing that's reoccurring. So there is now the ball on the left side, and now it goes to the right. Looks at the referee. The referee lifts his arm 5 times. It's just because of the way the video was cut. But now again, the ball comes into play, but we don't care about the ball. We watch the referee. So what's going on here? It's clearly not what was intended. What's going on here is that they have installed an automated camera in the stadium that will just automatically pan the camera around and zoom the camera around to get you the best image without a person being involved to save money. And this camera has an AI in it that was trained to detect the ball and to make sure that the ball is always in the picture and to zoom accordingly. And now there was a problem. The thing that they did not think about is that you might have a bald referee. And you might have the sun shining in such a way that the head of the referee maybe looks a little bit like the ball. So what's happening here is that this AI system thinks that the head of the referee is the ball and that it zooms to that. So this is going spectacularly wrong in this case. The camera is controlled by AI, and the AI does something incredibly stupid in a sense. And I took this video off YouTube, and of course of YouTube there's always very helpful comments. And this is the one I like best. I think we're safe from Skynet. So AI is pretty far away from being really dangerous because, well, if it can't like determine the referee, distinguish between the referee and the ball, it still has some things to learn. Nonetheless, AI systems are now used a lot, also in science. What you see here is the picture on the left-hand side is just a picture as it comes out of a microscope. And this picture is like from the life sciences, and it has a lot of cells in it. And one common task is to, if you, for instance, want to like establish whether cells grow very well in a certain medium or not so well, you like put many cultures in there, and then after a while you have to count how many live cells are in there. And this counting is something that in the 80s and 90s many PhD students had to do, and they spent a lot of their time staring through a microscope and counting cells. This picture had like 200 cells in it, the next picture 800, this picture only 20, and so on. And nowadays you can use a modern microscope, and you can have like an automated task with AI backing that basically like then colors the cells for you and says, this is a cell, this is a type of near cell medium, this is an intracell medium, and it can directly tell you this picture has that many cells and that many cells. And these systems very often, they work very well. So they're very useful tools. The problem we of course face is we have to predict, we have to know when the AI system goes wrong. And sometimes it's obvious, but sometimes it can be pretty subtle. So if, for instance, your AI system in your cell culture stops detecting one kind of cell because it was not trained in that kind of cell, then you might get wrong data. And if you don't notice this, you might draw the wrong conclusions. You might get wrong results. So you got to be really careful about what you want to do there. And then, of course, we have commercial interests coming in. The company that sells you that system, they might not be very transparent. They might say, well, this is our proprietary technology, so we will not give you the source code. We will not tell you how the system works. You have to trust that it works very well. And even if they give you the source code, if they give you all of those weights in these matrices, then full transparency might not even be enough. Because even if you have all of those numbers, how do you know what these numbers will mean? How do you know how the system will react in a certain way? In other cases, you don't have to know all of these numbers. You just have to like have a set of test cases, so full transparency might not even be required. So it's a complicated problem, and there's many people thinking about this at the moment. And this goes under the headline of explainable artificial intelligence, XAI. So the idea that your artificial intelligence does not only need to be able to make decisions and say, this is a cell, this is not a cell, this is a referee, this is a ball, but it also needs to be able to explain this decision to you. Because then you can build trust in it and say, yes, this is a good decision, this is a decision as it should be. Or you see where, okay, well, it's guessing on something, but it's not sure itself what's going on. And then you see where you have to be careful. So in some sense, people say you have to like take this black box of an AI system and turn it into a glass box. And this is an ongoing project where many people are working on many different approaches. It's a widely recognized problem. And let me just like show you two examples. So one example is something that Google did quite a few years ago now. It's called Deep Dream. So what Google basically said is, well, if I take such a network and kind of run it in reverse in a way, so I tell the network to amplify what it sees. So I tell the network, if on this picture now, you see a picture of some jellyfish, if you with, say, 1% probability detect a certain type of object, then try to transform the image such that you detect the object with 10% probability. So amplify the structure in the picture that tells you that this is what it is. And if you now take a network and you run this a couple of times, so it amplifies it in the feedback loop more and more and more and more, you can create something that you can almost call art. So what you can see here is now a very interesting structure. And if the system runs even more, you can see that there's clearly a lot of animal type shapes in the system. But you might think that, wait a second, this does not really look like jellyfish anymore. What's going on here? And clearly, this is a case where something goes wrong. This is a case where if I have a network that I have trained on dogs, it will see dogs everywhere because it's the only thing that it can see. So this network can be very powerful and detect dogs and all kinds of images, but it can never detect a jellyfish because it has not been trained on a jellyfish. So if I'm now a scientist and I'm looking at new things and I don't know what to expect, I also can't know very well what I should train my AI system on. So I got to be very careful. If my AI system tells me, yep, I've detected 5 dogs in this picture, whether it really has detected 5 dogs or whether there's something else going on that the AI system just doesn't know about this. So that's a problem. And these problems, of course, are not only problems in science, they're also problems in society, because AI machines are used in various different contexts. And let me just give you one example that's very recent. Everybody who's on Twitter has probably seen this. So this is a picture that somebody has created. It's one big picture with a rather elongated aspect ratio. So the middle of the picture is just white space. The bottom of the picture is a picture of Barack Obama. The top of the picture is a picture of Mitch McConnell. And then they posted that one on Twitter. And what Twitter does is, even if you posted a big picture, it will only take out a snapshot of the picture. It's kind of like the size of a passport picture. And it will try to show only that. And it will try to show the most relevant part of the picture, which in principle is helpful, right? If you have one person walking around the mountain, then you might want to just see that person in the picture, in the snapshot that it takes. So if they did this, then in the preview that you saw on Twitter, this is the left picture what you saw. So it took this long picture here, and it decided to basically focus on the white person at the top and show their picture. And now you can say, well, okay, maybe it just shows you the first picture that it finds, and it starts in the upper left corner. Could be. So as a scientist, what you do is you make an experiment. Let's make a control experiment. Let's take the same picture, but flip it around. Put Obama at the top and the other person at the bottom. And surprise, surprise. Again, it takes this picture. And then he went on for like many iterations of this. He said, well, maybe it's the red part here. Maybe you have to like wear red and then you get detected. So he like went into Photoshop and changed the colors, blue, red here. No, again, it's the white person. And Twitter admitted to this, and they admitted that this is something that they have not seen before, they have not expected, and they're very sorry about this. And I personally believe them that they were not racist by design, and they were not trying to be racist and only show white people and not black people. I think the problem was just that in the training set they used of pictures, maybe there was an imbalance there. Maybe there was like too many pictures with white people and not enough pictures with black people, or maybe because the pictures were typically taken in front of a dark background, say in front of grass or in front of trees, that then a white face just sticks out more than a black face. So it's maybe easier for the algorithm to recognize this. But whatever the cause is, it has consequences, and it has not nice consequences. And in this case, I don't think Barack Obama will mind very much that he's not shown as often on Twitter as he might be. He's still shown often enough. But if these algorithms are used also for various different decisions in society, for instance, if there's an algorithm running by your bank saying, well, you get the loan you want or you don't get the loan, and the algorithm can't even explain to you why you can't get the loan. It's just the algorithm says no, and we can't interpret it, then we have a problem. So also in society, we have to make sure that if we use these techniques, that we understand them, that these machines are interpretable, that these things can be explained, and that we therefore can build trust in them. So for scientists, that's something that we deal with every day. So for instance, this is again a picture from my group. And this is like a picture taken from the group of Marcus Kreiner and Harvard. And basically what's just going on here is that they can like take pictures and interpret these pictures. And here they see like a checkerboard type structure of an antiferromagnet. And they can take experiments, and we can do experiments in quantum simulations that nobody can classically simulate. So the experiment can now do things where you cannot classically check whether the machine is right or the machine is wrong. It's impossible because the machine is too complex. So we know how to deal with this. It's a complex but doable task. You have to like use test cases. You have to do cross checks. You try to do cross certification, cross verification. There's very many different things that we can do, but they all take a lot of time and a lot of effort. And what we have to make sure is when we start to use like AI techniques and all of this business, we have to make sure that we stick to these principles. We have to make sure that we stay in control of our software, that we avoid proprietary black boxes where we can't watch what's going on inside. And in particular, we avoid the associated non-disclosure agreements where we can't even talk about what happens in the algorithm. So we need to make sure that we continue to understand how we see. Thank you very much.
Thank you very much, Ulrich. Some wonderful stuff there, and a glorious image to end on. I'm actually no, I will. I was going to say I was tempted to ask you this, but I will ask you this, Ulrich. A picture like this. I mean, this is a stunning visual image. You could imagine an award-winning artist coming up with something like that as a great feat of creativity. Mm-hmm. Is it creative?
Well, you can take like various different approaches to that. You can ask yourself, how does your mind work ultimately? Can you be creative without external input? Or does creativity mean you build something out of input that you may even subconsciously have seen 10 years ago? And if that's the case, then of course, in some sense, also a machine, if it has a memory, can be creative. It's deterministic in the sense that it just the output now is based on all of the input it has ever gotten. But if it got so much input that you can't follow that, and that the relation between the input and the output is sufficiently complex, then why not? But in the end, of course, whether it's creative or not depends on what we define as being creative. It's a matter of mincing words in a sense. What do we mean with creative?
So having led us on that red herring or red doggerel or whatever the appropriate term for this picture is, just to remind you, there is an opportunity to ask questions. So either put them in a Q&A tab or raise your hand and I will bring you in to speak. We look forward to hearing your thoughts and questions on anything that we have here. And the first question that we have is from Paul Klein, who says, with the recent images of a black hole and the collisions presented by CERN at the LHC of the subatomic Higgs boson, how might visual configuration allow us to see dark matter? You know, we haven't detected dark matter, but what might it mean? How might we begin to see dark matter?
We are just gearing up on a project that has dark matter at one of its points. I would say, in a literal sense, we can never see dark matter, because seeing means that something interacts with electromagnetic radiation, and then we see this electromagnetic radiation, the light in our eyes. Because dark matter, as the name implies, does not interact with electromagnetic radiation, we can never see it. We can, of course, hope to detect it by looking at the influences it has on other parts of the universe, gravitational, or also very weak interactions that we hope to see using atom interferometry and atomic clocks.
Okay, the next question we have is from the very cryptically named NG. How would you, sorry, I've led us down this, how would you relate the creativity of AI with the creativity from the DMN?
From the?
DMN. I was hoping you knew what that was.
DMN. Well, as I said before, creativity is very... So again?
Default mode network.
Oh, because I'm not an expert on either of them, I probably can't possibly comment.
Just, you know, to step back a bit, you know, you've talked a lot about how we detect things. You know, we know atoms exist, you know, but we hypothesized them long before we could really demonstrate them. It always seems, but increasingly seems to me that there's a challenge for us all about how we know what we know. You know, you work on atoms, you've seen that, but there's no way that we can all verify all the things that we think we know. At some points, we always have to accept what other people say about it. How do we go about that? You know, is there a real risk of sort of epistemic security, if you like, about how we know what we know? And I say that partly in a scientific context where, you know, we'd like to think it's different from the political milieu, but there has been quite a lot of not very accurate publication. How do we sort of know what we can know and what we can trust?
Yes, I agree. I think it's there's a spectrum of possibilities, and physics tends to sit on the very easy spectrum of this, because the things that we're doing are very, very controlled normally. So if we do something where we really say we have a very groundbreaking result by one collaboration, by one team, by one scientist, maybe very surprising, maybe not what you would have expected, but groundbreaking, very, very important, then obviously we'll ask for replication. We'll ask for independent replication, or for somebody else with a totally independent apparatus, whether they see the same thing. So that takes a lot of those biases and ideas, of course, out. Now, that's a very comfortable position to be in, epistemologically speaking, in physics, because if you think of, for instance, I don't know, worst case climate science, you don't have this possibility because you only have like one set of observations stemming from one Earth. So you don't have like 100 Earths and you can see if I put CO2 on all of them, will they all increase or will only half of them increase in temperature? So physics is very, very easy in that case. But also in physics, of course, there is always methods of interpretation. And there's always a point where sociology comes into it. There are also the question of, okay, am I satisfied with the presented arguments and the presented observations, or am I not? And that's always something where people can have slightly different opinions on. So I think it's complicated and sociology comes into it, but I think physics is on the easy end of the system because stuff is relatively controllable.
So thank you. So I clearly messed up NG's question. So NG, whoever you are, I'm just going to allow you to talk, and then you should be able to ask the question, and then hopefully in a sense the way that Ulrich can answer, because I won't have messed it up.
Hi, how are you? This is the very cryptic NG. Can you hear me?
Yes.
Yes. Hello.
Awesome. Hi. Thank you for that wonderful talk. So my question is related to the first question that the moderator was asking about this jellyfish turning into something that's rather creative, and the way the default mode network of the brain works. You know, when we're in this sort of awake, unfocused phase where our creativity kicks in and we start to make connections that we didn't while we were consciously actively focusing and attentive and so on. And so when you start thinking about things like bias and interpreting whether AI is correctly interpreting or not, and the biases that we also have in our systems, and at one point it becomes how you can discover something that is before unknown or unseen because you're still making connections, versus how we do this with AI. This was kind of the question I was asking.
Okay. I think there's a lot of truth in that. I think the point is that at least if I think of myself as a scientist, how do I work? How do I think? How am I creative? It's a combination of the two things. There's a very creative phase where you start with free associations and some ideas just pop up. And you also can't really control or explain individually, in all cases, why you're not suddenly thinking of this idea, not that idea. But the point is that that's just like, if you want a noise source that's generating new ideas. The important point as a scientist is the step afterwards. It's the step of very rational, very conscious thinking hard about whether this new hypothesis, this idea fits the available data or not. So it's a little bit like, if I take an example from mathematics, when people solve differential equations. Very often you need intuition, you need like a guess what the solution might be, but then you can verify that this expression really solves the equation. So at that point, it's not important where the expression originally comes from. You can mathematically prove that it solves the equation, that it is a correct solution. And in some sense, with the hypothesis testing, you do the same thing. You're saying, okay, I have this hypothesis, wherever it comes from, and then I'm trying to like come up with all kind of tests that can discern this hypothesis from other ones. And then you run this whole arsenal of tests, and then you see whether it passes them all or whether it has to give way to another hypothesis during the way. So I think there's the creative part coming up with the ideas, and that can be uncontrolled. That's not so important. The important part for the scientists is that the second very rational stage, whether you internally accept this hypothesis or whether you very early on reject it. And I think also, if I'm thinking about the work in my lab, our apparatus is not working as it should. We come up with an hypothesis, what might be wrong, and then we test it. And then we come up with the next one. And very often only the 10th or 15th hypothesis is the right one. And that's normal, right? Einstein said, most of my ideas are wrong, and the main feature of my office is a really, really big basket case. Because I test my ideas and I throw the bad ones out, and then only a few remain.
So I'm conscious partly of time, and I know, Rick, you've got a huge amount to do to sort out everything else before lockdown kicks in at 1 minute past midnight. We do have another question. Going back to that beautiful image of the cosmic web, would you characterize that as having been detected or seen, or none of the above? What would you say?
I would say at some point, there is no difference anymore. If I have my bare eyes, I see something. If I have my bare eyes and a simple optical element, like your glasses, a binocular, you still see it. But as soon as this line of technology between the object and your senses becomes so large, at some point the lines blur and there's no difference really.
And of course, we haven't really talked about issues like visual illusions, where even just because you see something doesn't mean it's true. And there are some astonishing images of that where, where you see people of different sizes. I'll squeeze in one last question from a name that may be familiar to you, Ulrich, Tiffany Hart, who I hope you know, given given her. How can scientists improve people's trust or justify belief in seemingly abstract results?
Mm-hmm. I think scientists have to do two things. They have to not only explain the results, but they also have to explain the way to the results. They have to explain, like, a lot of the mental model. How do we get to this image? Why do we believe this is right and this is wrong? I think there's an awful lot of explanation needed. And I think there's a big challenge because a lot of this explanation, of course, needs time investment to make it well, but also to receive it and to think about it and to understand it. So how you can build trust with people that are not prepared to, like, invest that time of understanding what the scientists are saying, if the scientists pitch it appropriately. That is a challenge that we as a society, I don't know whether we know how to solve yet.
So I think, that's a very appropriate note, that challenge for scientists as to how we convey information, whether it's about a coronavirus and how we say what we know, what we don't know, whether it's about creativity, whether it's about massive things out in space or individual atoms in the laboratory. Ulrich, thank you so very much for joining us for this rather special night pre-lockdown. We will now leave you free to sort out everything else that I know you have to do to get the department in shape. And to everybody else, thank you very much for joining us. You have a bit more of an evening left. Please don't do anything too risky to celebrate your last night of freedom. And as George has just pointed out, you will be getting an online survey to find out what you thought about this. We hope to see you at other of our events. Thanks for being with us. Have a very good evening.